Hey, hello, my name is Carol. I'm a second year grad student at Harvard in Nauchida's lab. And I'm interested in using computational methods to study the neurotransmitter dopamine, and especially um, the function of dopamine related to decision making and learning and stuff. So let's jump into section 2, polynomial regression. So there are a lot of cases where linear regression is insufficient to capture the relationship between the features and outcome anymore. So here we have polynomial regression, which is saying that we can raise up the order of our feature to higher power, like quadratic or cubic, like second power, third power, so we can capture the quadratic relationship or cubic relationship between feature and output. So here's some example data. For example, in neuroscience, you can imagine Y is the firing rate of a neuron, right? And X could be a animal's motion kinematic, like it can be velocity. So here it's no longer in a linear relationship anymore, but more like a quadratic relationship, right? So if you imagine you draw a line to capture the most variance of all the dots here, you would probably draw something like this, right? It's no longer in a monotonic single line anymore. So let's jump into section 2.1, which is design a matrix for polynomial regression. Um, in this function, we have x, which is our input, order, which is polynomial regression order. So x can be a high dimensional data. This is x to zeros order, x to the first order, second order, even up to case order, right? There can be any number for the order here. So let's get to the code. The first two line of code is just to raise the dimension of x and make sure that it's not dimension one. And if it is dimension one, then we append a non-column, right? So it can be at least two columns here in our input data x. And first we for each row of x, we put one here, so that we have x to the zeros order. Okay, so this is what something we would want to see after we print a snippet of our design matrix. So this is one that we put in every row of our design matrix, and this represents x to zeros power. And then we would like to loop through the rest of the degrees and stack the columns. So here it suggests that we should use np.h stack. So this makes a lot of sense, right? Because eventually we would want the x to higher powers to stack horizontally, like something like this. So this is the first row, this is the second row. We want all the rows to stack horizontally together. So we already put x to zeros power here, and then we want loop through for x to the first power, second power, third power, etc. So here we as it suggested, we should use np.h stack. The autocomplete already fills the code for me. Let's see if it makes sense. So this is the design matrix with x to the zeros power that already filled in for us. And then we wanna put x to higher degrees. So it's something like this. So eventually we would horizontally stack them together. So let's comment out this. Okay, perfect. It matches what we expect to see. Here we only see two columns and two rows here because we only print out two columns, two rows. And we can print more if we want. Okay, that's it.